So this talk, basically, some of you may feel that, okay, this is a little more on the hardware oriented, but I'll try to keep little simple so that everyone understand that, right? So here there are a few terms on the subject itself, C7x. So C7x is nothing but a DSP, which is from the Texas Instrument, which has basically vector core and the MMA core for DSP processing, as well as your neural processing unit is there. Okay. Okay, so few things about TI. We are the upstream first vision we have. Most of the things we do with upstream. Most of our codes is available in open source. We work with the different open source partners like Linux Foundation, Yocto, then we have the OpenAMP, Jyper, OpenCL, KernelCL, all those things we work. So agenda for today's talk is that first we talk about what is the problem statement which we are trying to solve, what is the proposed solution, the software architecture of the proposed solution, and one example we'll take how the Linux controlled multi-channel audio we are offloading to DSP and how we are basically measuring the performance, the improvements we are seeing over there. And then we'll talk about the current status, what we have, and what is the next plan for that. And at the end, we go for the Q&A. Some disclaimer, basically, this is the, as you say, it's a technology presentation. It's not for the product readiness or roadmap commitment. Opinions here, whatever we are presenting, it's speaker opinion, not the TI itself, right? And some of the visuals which are there in this PPT is basically generated using AI tools. However, all the performance data is based on the actual measurement results. Okay, so let's talk about the problem statement. See, this talk is about how we offload the compute on the DSP, whether this compute we do on the ARM core itself or we do on the DSP. There is certain problems if we do on ARM only and if we do only on the DSP only, right? So first thing is that when you are doing it on ARM, right? So the inefficient CPU usage. Basically, ARM is not designed for the high compute real-time workloads, which basically leads to high CPU usage, right? So that is the one problem where we cannot run all our DSP algorithms on ARM core itself, right? Second problem, if you are using Linux with DSP, so there is like different basically complex integration involves when you are doing this. So that basically when you're interfacing the Linux with the DSP, it involves custom IPCs, or memory handling is the problem, the synchronization, all those are very complex. So in this talk, basically we are trying to propose a solution which can simplify all these things, right? The second is the poor scalability, right? So system is basically bound to your CPU usage, right? When you have the multi-channel or audio or whatever, it takes like too much bandwidth of the CPU and it may not be available for let's say the graphics, your UI or the control, all those things, right? So that's why it is basically limiting the performance or the scalability for DSP algorithms running on. The next is the inefficient data movement. Since we have to offload let's say your audio crossing to DSP, then you have to move the audio data to DSP, which basically is problem because you have to create multiple copies or unmanaged buffers, which will involve your latency, overhead, all such things over there. The next is the underutilization of the DSP resources. DSP core basically is there, but they are underused due to integration difficulty, lack of simple workflows. Because if I want something to use from the Linux or ARM core, it on that time not highly utilize the DSP core resources, right? So that's the problem. So what we are trying to see, existing solution usually trade off simplicity for performance. The problem is not here the DSP compute availability. It's basically making the DSP compute usable from Linux in a simpler way with keeping the performance and latency at the same time. Okay, let's talk about the proposed solution. So where Linux controls, you have the network, you have the display, you have your ADC, DAX, all those things there. So Linux here controls all those things. You have the control which is on your GUI. You want to turn off a specific filter, you want to turn off the EQ, all those things you can do using the Linux control, right? DSP role here is just to accelerate, right? Whatever the DSP algorithm you want to process, let's say you want to do the noise cancellation, right? Noise removal, all those things you can give it to DSP so that it can just accelerate those things and give you the result, which you can use on the Linux side on your application. So core idea here, as I said, so Linux we are keeping as an orchestrator, and DSP is basically to compute the accelerator. So we separate here in two parts, the control and the data plane. So control plane is basically on the Linux, and the data plane is basically your shared memory, where the data is copied or sent to the DSP using the shared DMA buffer memory. If you see this diagram, basically you have the A core where your Linux application is running. You have the different framework like ALSA framework, and then we have the RPMsg DMA library. So this is the very thin library which basically provide you the control information where you and buffer management. This is used for the communication between ARM and your DSP using the RPMsg or RPC, whatever you say, and it allocates and manages the shared DMA buffers, which is used for the data transferring between A core and your DSP. It handles synchronization and low latency messaging, right? So here in this, we are basically emphasizing on the zero copy buffer. We don't want to have the multiple copies when we are sending from the Linux to DSP. It's a single buffer where the Linux or your application will write that to DMA buffer. It notifies to the DSP using the RP message. It's just notification. You see the control plane is here. It just notifies, okay? There is no actual data transfer happening from A core to Linux core, right? So DSP basically, once it receives that, the RP message or control message, it basically copies the data from this shared DMA buffer to L2S RAM. So here one important thing, why the L2S RAM is coming. It is internal RAM to DSP, so it basically improved the overall compute performance. So that's the reason this is copied here for internally, right? So DSP, when it executes the signal channel chain, it basically execute in the L2S RAM. Once it is done, right, it copy back the data to the same DMA buffer and notifies to the A core that the processing is complete, right? So this is how the overall things are here, right? So what is the advantage of using this? What problems we are solving, right? So there is no need of moving any application logic from your Linux application or Linux side to DSP. Everything remains same. Only the control path and the messaging part will take care of the offloading to DSP, right? So we can reuse the pre-built DSP kernels. So whatever the DSP kernels are there, you can just pre-build and use it. There is no what you say runtime DSP kernel compilation or happening in the DSP side, right? As I said, it's a zero copy buffer model, so no redundant ARM or plus DSP copies are made. It's a single buffer, so that saves the memory as well. With this, we can achieve the deterministic low latency processing. So the processing latency is still remain the same in this case, right? It's a clean, reusable, and heterogeneous compute platform, right? So we have the different heterogeneous platforms available where you can, using this simple framework, you can achieve the deterministic low latency processing for your workloads. So let's talk about the software architecture, right? How it is there. As I said, you'll have the Linux user space here where you have the audio applications running, where you have the audio pipeline using ALSA, GStreamer, or custom app, whatever is there. And then basically in this architecture, I'm showing when you are offloading the audio data to DSP for processing, right? So if you see this application is for in the copying the data to the shared memory, right? And here we have this very thin, lightweight TI RPMsg DMA library, right? Which basically allocate the DMA capable shared memory buffer in DTR. It manages the RPMsg control and enable the zero copy audio transfer and handle the synchronization, right? So this library talks to your Linux kernel drivers where we have the remote proc RPMsg drivers, which basically talks to the DSP core, right? And the DSP core side, DSP firmware, which is running on the C7x, as I said, it's a TI own DSP, right? And then which will basically receive the RP message notification, and at the same time, it will also send the RP message back to the Linux TI RP message library and back to the application. So once it receives the DSP firmware, basically receives the notification to do the processing, DSP will have your audio DSP kernels where you have the signal chains, where it will do the copy that audio data from the shared memory buffer to L2S RAM, and then it does the processing and write back the processed data to the shared DDR, and then basically your DSP firmware will notify back using the RP message. So if you see here, we are clearly dividing the control plane and data plane in this architecture. So here the control plane, you can see this is there, and your data plane is completely separate. It's not in one plane, and there is no copy of data or anything happening in this one from the your Linux side, A core side to C7 side. It's a shared DMA buffer where everything gets done and there. Okay, so let's take one example over here to demonstrate how these things are working, right? So I'll take the Linux control multi-channel audio offload filtering example. So when I say multi-channel, in this example, we are doing the 8-channel audio. If you run this on the normal ARM, you will have the very high latency, and that's what we are trying to achieve. The latency should be reduced, and as well as the load of the ARM core should be reduced, right? For this particular example, we have used the TI M62D EVM SoC. So what exactly is this one? So this is the 62D is basically a premium audio and signal processing SoC, which has the basically for the premium audio, you can connect the Class D amplifiers on this 16-channel Class D amplifiers. It has onboard basically 4 DAC and 2 ADCs, which supports onboard 8-channel recording as well as 8-channel playback. It has the Cortex A53 running Linux. It has the C7x Vector Plus, Vector DSP Plus. We have the NPU, which runs on 2 tops available in this one. It has the R5 cores, which is basically for real-time control, device management, and as I said, the Mac ASP interfaces for multiple audio to support. So in this device, we can have, theoretically, we can have the 16 plus 16 channel audio. So hopefully this is visible, yeah. So this is one of the example I'll quickly show. Here, basically, the A core application, it will read the 8-channel audio from the SD card. It can be directly from the 8-channel the ADC ports. It reads the data. It basically sends, is basically copy the data to the DMA buffer, whatever shared DMA buffer is there. Then it's using RP message. It's sent to C7. C7 basically receives on acknowledgement. It basically copy the DMA buffer data to L2S RAM. Then it executes the signal chain. And then after execution, it basically copy back the data from L2S RAM to DMA buffer, and then it notify using RP message back to A core, where this A core can basically play the data, 8-channel data to the DACs available over here. At the same time, you see here, we have the RJ45 or serial connection, using which basically we can monitor and control the operations on DSP. We can see the live throughput, what's happening on the ARM, what is the latency, what is the DSP usage, all those information over here. So let's talk a little bit on the signal chain, what we are executing over here. So here, once the data is received on the C7 side, right, it basically converts sort to float. It has the cascade bichord low-pass filter with the cutoff frequency of 10 kilohertz. And after that processing of this filter, it's sent to the high-pass filter, which is basically 2 kilohertz cutoff frequency. And then it uses the matrix transpose and then send it to FIR low-pass filter with the cutoff frequency of 8 kilohertz. And then it does the real FFT and then IFFT and matrix transpose and the float to short. And after that, this data is copied back to DDR so that the Linux can basically use this data to directly to play. Right, so before that, I will just see if I can show you the real example, right? How it is there. So, sorry, it's connected to VPN, so it may be a little slow. I'm just trying to run the application, the Linux M62D EVM, right? And this is basically connected to the host machine visualization tool. So here, You can see this is the 8 channel. Right now we are displaying the 1 channel data over here. So, okay, so you cannot hear the audio because this is connected on the mice setup where the it will be playing on the board. So you cannot hear the audio, but here you can see the live, basically the how many frames you are processing, what is the latency, the amplitude, CPU load, DSP load, right? And at the same time, it has the control of basically you can turn on or turn off the filtering operation, which is the basically the DSP operation, right? So let me quickly do the turn off. Sorry. Okay. So now the filtering is off, right? Okay. Just a second. Let me quickly run. Sorry for this. Okay. So yeah, now it's running. I will just see this control. It's okay. So you can see here now this it is turned off the DSP execution. Now you can see the basically the load get higher on the CPU side, and the DSP load will basically will get 0. And if I do again the now you can see the amplitude over here, right? When it was running on the ARM, it was fully there. Now it's basically the filtering is happening. You can see this ARM amplitude was getting lower there, right? Sorry, this is because of the VPN connection, it's getting slow. So I'll come back over here. Oh, this all information is available on our documentation part for the 6-2D example. Okay. Okay, so let's see the performance comparison, how it is there with ARM, running everything on ARM versus running on the C7x plus ARM, right? So ARM only we are saying the latency is around 2.04 millisecond and CPU load is around 37%. It is basically CPU bound and limited scalability. If you have the multiple channels running on this A core itself, that will be causing problem, which will not have the enough bandwidth to run any other application, GUI and other things. When we are running on the ARM plus C7, we can see the latency has 6x improvement. It's coming around 0.33 milliseconds and CPU load reduced to 21%, which is basically around 43% reduction. So, and DSP load is around 7%, which gives the enough room for running anything else on the C7 DSP as well. So that's what we are saying. Basically, this DSP offload mechanism, what we're showing, it transforms system performance from the CPU bound to scalable, reliable, real-time system, right? The signal chains, what we were showing here, this is not strictly identical, but the result reflects the system level improvement with DSP offload. Okay, let's go to the current status and plan ahead. So current status is that we have the complete DSP offload architecture available. We have all the library frameworks, the buffer management, zero config data, all this available with ALSA. We have the achieve end-to-end real-time multi-channel processing pipeline, DSP execution on L2S RAM for optimized latency. And next step is basically we integrate this with the Pipewire, the modern Linux audio stack with GStreamer, right? And the main part is that we want to extend this to DSP plus AI hybrid pipeline, where we run the analytics on the DSP core for feature extraction and inference. Basically, let's take example of your audio conferencing where you want to have the noise suppression right? At the same time, we want to know where exactly the speaker is present, how many speakers are there, all those kind of things we can do using this framework. So that is the next stage we are going to do. We want to enhance the scalability for higher number of channels, bandwidth, and workloads, improve buffering and scheduling, and add some more information on how to profile tracing and latency measurement tools, etc. Yeah, there are some references which you can refer it, which has all the information. As I said, TI, we focus on open source upstream first, so everything is open source. You can go through these links, references, and get all the information from there. Okay, so little bit on the credits, basically from the Bharat Ramesh from TI C7x DSP team for the DSP side kernel implementation part, then Anup Krishnan from the TI AM62D RTOS team, and obviously the Texas Instrument itself to giving this opportunity, right? For any thing, you can reach me at my email ID is given over here, and our IRC channel is there. That's all for my talk. Please, if you have any questions, let me know.